Before you is one of the fastest objects in the universe. Its rotational speed is hundreds of times greater than that of a helicopter's blades, and its mass is nearly 2.5 times that of the Sun. Yet, despite this immense mass, its size would allow it to easily fit within the boundaries of New York City. This is Pulsar J09520607, the heaviest neutron star ever discovered by scientists. It spins at 707 revolutions per second. That's faster than the blades of your kitchen blender or an aircraft turbine, faster than anything you can imagine. But what makes it spin at such an incredible speed? It requires energy, and the Pulsar has an energy source, a white dwarf, the remnant of a star that once shone but has now fallen victim to its companion. The white dwarf is too close to the Pulsar. Due to the immense gravity and powerful radiation, its matter begins to strip away, turning into a stream of superheated plasma that rushes directly toward the neutron star. The Pulsar absorbs this material, gaining even more energy for its rotation and radiation. Meanwhile, the white dwarf rapidly loses mass, becoming dimmer and weaker. It's practically evaporating, surrendering its matter to its more powerful companion. But this process is dangerous even for the Pulsar itself. Gradually, it accumulates matter and approaches its critical mass. If it exceeds this limit, its matter will no longer be able to resist its own gravity, in which case the Pulsar risks collapsing into a black hole. A neutron star is one of the most exotic objects in the universe. Its formation is an event of galactic proportions. Every time a massive star, at least 8 times the mass of our Sun, exhausts its nuclear fuel, the thermonuclear reactions in its core cease. The core can no longer withstand its own gravity and begins to collapse at an incredible rate. This causes its temperature to soar to billions of degrees. As a result, the star's outer layers expand and cool simultaneously, turning it into a red giant. When the temperature and density in the core reach a critical point, a supernova explosion occurs. Afterward, all that remains of the once massive red giant is its core, now a neutron star. The mass of a star like this is typically around 1.4 times that of our Sun, but its size is truly astonishing. Its radius is only 6.2 to 7.4 miles, nearly 70,000 times smaller than the Sun's radius. Imagine the Sun shrinking in size until it becomes a sphere small enough to fit within New York City, which is about 35 miles wide. Compressing an object 870,000 miles in diameter into something just over 6 miles across has a massive effect on the matter that makes up the object. Neutron stars are a striking example of this. According to NASA, just 1 teaspoon of neutron star material would weigh about 1 billion tons on Earth. That's equivalent to the mass of 3,000 Empire State Buildings or the entire human population. This makes neutron star material the densest substance we can observe in the universe. It has such an unbelievable density that if, under some fantastic circumstances, a piece of it the size of a sugar cube was placed on Earth, it would instantly punch through any surface, drilling downward through the layers of the planet until it reached the core. Compared to this, the density of everything around us is practically negligible. Another astonishing property of a neutron star is its temperature. On average, its surface is heated to 600,000 to 1 million degrees Celsius, and right after its formation, it can reach a mind-boggling 10 million degrees Celsius. That's about 1,800 times hotter than the surface of the Sun. Yet, despite these extreme temperatures, the surface of a neutron star remains solid. Scientists believe it's covered by an iron crust about 0.6 miles thick. What lies beneath remains a mystery. How matter behaves under such temperatures and pressures is impossible to replicate in laboratories, leading to various theories. Some scientists suggest that inside neutron stars, protons and neutrons break down into even more fundamental particles called quarks. If true, the depths of these objects could be composed of a mysterious quark matter. Another mind-blowing feature of neutron stars is their immense gravity, caused by their extreme density. The gravitational pull of Jupiter or even the Sun, which holds an entire planetary system in orbit, pales in comparison to what happens near a neutron star. Its gravity is beyond comprehension. To grasp the extent of its power, imagine your spaceship somehow landing on a neutron star's surface. To take off and escape its gravity, you would need to reach a speed of 93,000 miles per second, half the speed of light. For comparison, escaping the Sun's gravity only requires a speed of 383 miles per second. If by some fantastical means you dropped an object weighing less than a pound onto a neutron star, it would accelerate so much upon impact that the energy released would be equivalent to the explosion of 1,000 hydrogen bombs. The only stronger gravitational pull found in the universe belongs to black holes. Neutron stars are so incredible that they're rightfully considered among the most exotic objects in the universe. However, as it turns out, they come in a variety of types, and some are so unique that when scientists first discovered them, they thought they might be signs of extraterrestrial life. In 1967, British scientists detected a strange phenomenon. Something or someone was sending signals to Earth from space. These signals arrived with astonishing regularity, as if something in the distant cosmos was switching on and off with precise timing. At the time, it was interpreted as a possible message from extraterrestrials, since nothing known at the time could produce such signals. Later, it turned out that these signals came from a pulsating radio star, an object emitting rhythmic pulses, which is how pulsars got their name. A neutron star is not only an extremely dense and incredibly hot object, but also one that rotates at an extraordinary speed. This effect arises due to the conservation of angular momentum. To better understand how this works, imagine a figure skater spinning on ice. When they pull their arms close to their body, their rotation speed increases dramatically. A similar process occurs with a neutron star. As a star collapses under gravitational forces, its diameter shrinks and it begins spinning faster and faster, reaching dozens of rotations per second. Over time, neutron stars generally slow down, reducing their spin to about 8 rotations per second or even less. However, if a neutron star has a companion, such as a white dwarf, the situation changes. By absorbing material from its partner, the neutron star retains angular momentum, which can accelerate its rotation. This spinning acceleration effect can make some neutron stars rotate dozens or even hundreds of times faster than regular isolated neutron stars, transforming them into pulsars. As they spin, pulsars emit powerful, destructive beams of energy from their poles, producing sweeping lighthouse beams composed of radio waves, visible light, X-rays, and gamma rays. The flashes from these beams are detected on Earth, creating a cosmic beacon effect that resembles an artificial signal sent from deep space. Moreover, pulsars pulse with astonishing precision, allowing them to function as highly accurate cosmic clocks. Some are so stable that their periodicity rivals atomic clocks. It's hard to imagine an object with a radius of just 6.2 miles spinning faster than helicopter blades, but this is far from the limit for neutron stars. In the distant Sextans constellation, 5,000 light-years from us, scientists have discovered a true monster, making ordinary neutron stars seem almost tame in comparison. Its name? PSR J09520607. This is the heaviest and one of the fastest spinning neutron stars ever discovered. Normally, neutron stars have a mass of around 1.4 times that of the Sun, but this pulsar's mass is nearly 2.4 solar masses, bringing it close to the point of no return. According to recent calculations, if a neutron star reaches a critical mass of 3 solar masses, it can no longer resist its own gravity and will ultimately collapse into a black hole. If a neutron star rotates at a normal speed, say no more than 30 times per second, it only needs a mass slightly above 2 solar masses to collapse into a black hole. However, for pulsars, the situation changes. Rapid rotation increases a star's resistance to collapse. PSR J09520607 is one of the fastest pulsars ever observed, spinning at an astonishing 707 rotations per second. For comparison, the blades of your kitchen blender spin much more slowly. Thanks to this immense speed, the pulsar continues to resist turning into a black hole, but this does not last forever. For a long time, scientists sought to understand why this neutron star spins so fast and has such a massive weight. All the data suggests that it must have a stellar companion from which it actively accretes matter, increasing both its mass and rotational energy. This hypothesis was confirmed. Orbiting the pulsar at 236 miles per second is a companion star, likely a white dwarf, being slowly devoured by the pulsar. This process will eventually lead to the complete destruction of the white dwarf. Pulsars of this type are called black widows because they consume their stellar partners, growing more powerful in the process. However, everything has a limit. Even before fully absorbing its companion, PSR J09520607, given its mass approaching the critical threshold, will likely collapse into a black hole. A supermassive, rapidly spinning pulsar like this has the potential to obliterate anything caught in its gravitational field and intense radiation, including the solar system. If J09520607 were to appear in orbit around Mars or Jupiter, the closest planet would be its first victim, torn apart and consumed by its accretion disk. The remaining planets would be thrown off their stable orbits, chaotically drifting toward the pulsar. Earth would be doomed too. The atmosphere would instantly evaporate, and the surface would turn into a scorched, lifeless wasteland. Eventually, the pulsar would devour the Sun, and upon nearing 3 solar masses, it would collapse into a black hole, wiping out the remnants of what was once the solar system. However, even such an incredibly dangerous cosmic killer has rivals that surpasses it in certain aspects. One of them is located just 1,000 light-years away. We're talking about one of the brightest pulsars ever observed and one of the closest to Earth. This pulsar is known as Vela, and astronomers recently detected the most powerful light burst ever observed coming from it. Studies of Vela have shown that its gamma radiation is about 200 times stronger than that of an ordinary pulsar. This suggests that something unusual is happening within its pulsating polar streams, which extend 0.7 light-years into space, a distance 15 million times greater than that between Earth and the Moon. Normally, particles accelerate with specific zones around a pulsar, but these regions alone cannot explain the extreme energy levels observed in Vela. Scientists speculate that particle acceleration may occur beyond these usual zones, or that powerful magnetic fields exist outside them. Another possibility is that neutron star winds accelerate particles, ejecting them with enormous energy. The scientific community has yet to reach a consensus, and research into this pulsar is ongoing. One particularly fascinating discovery is how Vela would sound if its signals were in the audible range for humans. Like other pulsars, Vela emits regular radio bursts, pulsating approximately 11 times per second. NASA scientists recorded these signals using a radio telescope and converted them into an audio format. The resulting sound resembles the whir of helicopter blades or the roar of a car engine. Since Vela is relatively close, scientists have also been able to study its incredibly powerful magnetic field in detail. Neutron stars are known for their colossal magnetic fields. Vela's, for example, is 2 trillion times stronger than Earth's. But imagine, there are neutron stars in existence with magnetic fields 1,000 times stronger than Vela's. These stars are among the most dangerous objects in the universe. Their power is so immense that if a person were to be just a few thousand miles away from one of these stars, Their body would instantly dissolve into space under the influence of a colossal magnetic field, which would disrupt the atomic structure of their body. They're called magnetars. This is an extremely rare type of neutron star. Only 1 in 10 supernova explosions gives rise to a magnetar, a celestial body possessing an unimaginably strong magnetic field, the most powerful in the entire universe. These neutron stars can generate gamma-ray and X-ray bursts, releasing colossal amounts of energy. The strength of their magnetic field is so great that it causes a unique phenomenon: the slowing of the star's rotation to just 1 full turn every few seconds, or even minutes. Moreover, even the magnetar itself cannot withstand such extreme magnetic fields. Periodically, these fields cause starquakes on the surface of the magnetar. These quakes make the star's solid crust crack and shift, releasing an enormous amount of energy from its depths. This makes the magnetar unstable and, at that moment, more dangerous than ever. During these events, the energy ejected from its core in mere milliseconds can equal the energy the Sun emits over an entire year. If a magnetar were just 10 light-years away from Earth, the radiation from an explosion like that would instantly destroy our planet's ozone layer. Fortunately, the closest known magnetar, XTE J1810197, is located 8,000 light-years away, meaning Earth is in no danger. However, if it were just a little closer, our concerns would be justified. If this magnetar experienced a starquake within 4,000 to 6,000 light-years of Earth, the intense burst of gamma radiation could partially affect our atmosphere. The first problems you'd notice would be power outages and interference in your car's navigation system. While trying to figure out the cause of the disruptions and avoid getting lost, Earth's atmosphere would be under siege by high-intensity gamma radiation, causing severe damage to power grids and satellite communications. The consequences would be even more catastrophic if the magnetar were even closer. But what if, theoretically, a magnetar took the place of our Sun? Let's imagine that an 8-mile sphere with 1.5 times the mass of the Sun would replace our parent star. However, you wouldn't have time to realize that the Sun had dimmed strangely. Your death would be instant. A magnetar's magnetic field is a quadrillion times stronger than the Sun's. It would instantly strip Earth's atmosphere, leaving it unprotected against extreme radiation. The radiation intensity would be so immense that it would break the chemical bonds of most elements. Everything would be thrown into chaos, and the closer you are to the magnetar, the more catastrophic the consequences. Mercury would be the first victim. The magnetar would alter its orbit, pulling it in. Under the influence of colossal gravitational forces, the planet would begin to deform and break apart. As it approached within a few thousand miles, Mercury would be completely torn apart into atoms by the magnetar's ultra-powerful magnetic fields. Venus, Earth, and Mars would soon follow, meeting a similar fate. As for the gas giants, their orbits would be disrupted, but they might just stand a chance of survival. It all depends on how long the magnetar remains active. Its energy could be depleted before it has the chance to completely incinerate the remaining planets. Magnetars burn through their energy incredibly fast, and after about 10,000 years, they begin to lose their powerful magnetic fields and quickly fade. This is another reason why these objects are so rare in the universe. Pulsars, on the other hand, can exist for much longer, billions of years. This gives them enough time for rare and unexpected events to occur. For example, even such an extreme object as a pulsar can acquire its own planetary system. PSR 1257+12, located 2,300 light-years from the Sun, has 3 planets that belong to the super-Earth category, rocky planets with masses several times that of Earth. Another pulsar that was not doomed to loneliness is PSR J2007+3120, which has at least 2 exoplanets in its system. Both are several times more massive than Earth and complete an orbit around the pulsar in 1.9 and 3.6 years respectively. This is a rare phenomenon. Out of the thousands of known exoplanets, only about 15 have been found in pulsar systems. In fact, only 0.5% of all pulsars are known to have planets. It's difficult to imagine the extreme conditions that might exist in worlds like that. The chances of surviving there are almost non-existent. But if life did exist on a planet in a pulsar system, it would be like a wild teenage party. Bright, painful for the eyes, and carrying a high risk of death. Additionally, all planets in pulsar systems share a common trait: highly elongated orbits. For example, in our solar system and in most others, planets typically follow nearly circular orbits, while planets around pulsars move in highly elliptical ones. This doesn't exactly explain how such dangerous objects manage to form planetary systems, but scientists have some theories. It's believed that these worlds may form from material ejected during the supernova explosion that created the pulsar, or from the remains of a companion star that was consumed by the neutron star. It's also possible that pulsars can capture planets passing nearby due to their immense gravity. For now, this remains a scientific mystery. While you were watching this video, more than 100 supernova explosions occurred in the universe. Some of them left behind neutron stars, while others turned into black holes. These events continue to shape the cosmos, creating new mysteries for us to unravel. We've all seen the solar system pictures in textbooks. The Sun slightly larger than Jupiter. But that isn't the right depiction of the scales. The Sun is so massive that you could fit about 1,000 Jupiters inside. Impressive as it is, our Sun isn't the biggest star in the universe or even our galaxy. That title goes to UY Scuti, and compared to it, our star is like a tiny pebble. But there's more. Scientists have stumbled upon something even more mind-boggling. An enigmatic ancient star with a black hole inside. It's an astronomical mystery that both puzzles scientists and can potentially explain how the universe came to be what it is today. But how is it possible for a black hole to exist inside a star? Stars are like cosmic blacksmiths. In their fiery cores, they're forging the majority of the elements we observe in the universe. But the stars that could have existed at the very beginning of the universe were something different. Instead of conventional stellar cores, they harbored black holes within, allowing them to grow to unimaginable sizes and beyond. Ordinary stars arise from the clouds of gas and dust as gravity makes the densest regions of the cloud collapse. The resulting mass of material heats up and creates a protostar, an early stage in the evolution of a star. Eventually, the newly formed hot core accumulates enough matter from the surrounding rotating disk of gas, becoming a main sequence star that starts producing energy through nuclear fusion. It took our Sun about 50 million years to reach this phase. The majority of stars will spend most of their lifespan as main sequence stars, but eventually they will either become white dwarfs if their mass isn't big enough or go supernovae. After a star blows up, it can end up as a black hole or a neutron star, and the path it takes depends on how massive it was. When our Sun runs out of hydrogen in about 5 billion years, it will turn into a red giant, expanding 200 times in size before finally shedding its outer layers and transforming into a white dwarf, a celestial object that's roughly 200,000 times denser than the Earth but about the same size. This dense sphere will slowly cool to about 18 million degrees Fahrenheit, and in about 10 billion years, the white dwarf Sun will crystallize. The process is somewhat similar to how water turns into ice. Although the material is different, in the case of the Sun, it will be carbon and oxygen solidifying. And stars over 10 times the mass of the Sun will have a different fate. They're big enough for their cores to collapse after a supernova, but they lack the mass required to become black holes. So where does this leave them? Deep inside these stars, the extreme pressure squeezes every proton and electron so tightly they merge to form neutrons. Neutrons cannot be compressed any further, so they counter gravitational pressure and the star finds a new balance. Neutron stars are the densest objects in the universe apart from black holes. They can be just the size of a small city, roughly 12 miles, but still have a mass of the Sun. On Earth, neutron star material the size of a sugar cube would weigh as much as 1 billion tons, about as heavy as a mountain. But how do stars become black holes? While the star is still active, the two prevailing forces work against each other: nuclear fusion and the intense gravity created by the star's own mass trying to squish it. Once there's no fuel left to power nuclear fusion, there's no longer a force to counter gravity, and the star collapses on itself, just like the controlled demolition of a concrete building. Einstein believed that anything could become a black hole if it had sufficient mass and was compressed inside a certain radius. Black holes keep on growing throughout their lifespan, devouring any material that gets too close. When this happens, the region where gravitational pull becomes so strong that nothing can escape increases, and the black hole consumes even more nearby material. It's somewhat like the sinking of ground due to the collapse of underground structures. Although with black holes, it's a gravitational sinkhole, gradually accelerating as its event horizon grows. Normally, black holes have a limit on how fast they can expand. This happens because of something called the Eddington luminosity limit. Basically, it's the point at which a black hole can't take in material faster than it already does. If you were filling a car tire with air and it had small holes in it, the increased pressure inside would make some of the excess air escape. In space, something similar happens with rotating black holes. As matter spirals towards a black hole, it goes faster and faster. Because of this, about 42% of this matter can be converted into energy. And this radiation is so powerful, it can push some of that incoming material away, just like a car tire pushes the air away. This process is so efficient, the radiation emitted away surpasses the energy output from nuclear fusion in stars. Just imagine a future where we find a way to harness this energy and use it for our needs. Even supermassive black holes with a large surface area that attracts matter have this limit. They are at the center of almost every galaxy out there, and some of these supermassive black holes have been recently discovered to be much larger than we thought. That's one of the greatest mysteries in astronomy. The gradual accumulation of matter over the edge of the universe fails to explain their enormous size, but there's something that might unravel the mystery. Black hole stars, or quasi-stars, must have been the largest celestial bodies to ever exist, dwarfing even the most gigantic black holes we've discovered so far. Today, the conditions of the universe do not allow black hole stars to form. But at the beginning of time, space was packed with massive gas clouds. Within these dense regions of space, material collapsed in on itself under its own gravity, and because there was so much of it, it piled up, giving rise to baby stars of extraordinary magnitude. Although there's an idea that they may have originated from dark matter halos, invisible spherical regions of dark matter of up to 100 million solar masses where thousands of supermassive stars could form. Normally, large stars would go supernova and leave behind massive black holes. But these celestial giants weren't just large, they were so huge, their size allowed them to absorb the explosive force that would otherwise shoot the star's outer layers out into space. Instead, these ancient stars only experienced implosions, which transformed their stellar cores into tiny black holes, while keeping the outer layers intact. If you could somehow observe this phenomenon from a close distance, you wouldn't even notice any changes within the star. Now that there's a baby black hole inside a quasi-star, it starts eating it from the inside. At this point, the black hole is tiny, but it's spinning, and this creates a disk of hot material, circling it at nearly the speed of light. On top of that, there's no longer a limit on how fast it can devour gas, as the star's pressure sends it straight into the black hole. The friction within the accretion disk becomes hotter and hotter, emitting tons of radiation and making the hot star glow like a small galaxy. Quasi-stars, if they existed, grew faster than any black hole we've ever observed. Eventually, within millions of years, some of them would be the largest stars and black holes in size that we know about, like Stephenson 218, UY Scuti, and Ton 618. Just how large is that? From thousands of times larger than the Sun to potentially even the diameter of our solar system and beyond. But this gargantuan size and mass also causes problems. The larger the quasi-stars become, the shorter their lifespan. Our Sun has been around for over 4 billion years, with approximately 6 billion years left in its lifespan, while black hole stars lasted for just a few million years before spectacularly exploding with unprecedented power, releasing an ever-hungry, monstrous black hole ready to drift across space in search of more material to gobble up. But what if a star like this wandered into our peaceful celestial neighborhood? Once a quasi-star found its way into the solar system, its gravitational influence would disrupt the established orbits of planets and celestial bodies. The once orderly planetary system would be in total chaos, with Earth experiencing a severe asteroid rain. The effects would start before the quasi-star entered our solar system completely. As the gigantic star swallows the outer planets and other celestial bodies, our planet would already experience a surge in temperature and luminosity, making the surface inhospitable, until finally it would consume the Earth too, although life here would long be gone by then. The central black holes within quasi-stars could have served as seeds for the formation of supermassive black holes that are at the centers of galaxies today. And they might have even played a bigger role. The dynamic processes associated with quasi-stars, such as the collapse of the central black hole and interaction with the surrounding matter, could be potent sources of gravitational waves, which in turn may have played a role in the formation of galactic structures and the distribution of stars within galaxies. But not just that, quasi-stars could have implications for astrobiology. The intense radiation from these objects might have affected the habitability of planets in their vicinity, potentially shaping the conditions for life in unexpected ways. That said, in the context of cosmic evolution, quasi-stars might have set the future by shaping the early universe in unthinkable ways. But here's another mind-blowing thought for you. Although there are probably no quasi-stars in our universe today, tiny black holes roughly the mass of an asteroid from the dawn of time might still be here. Theoretical physicists speculate that if such black holes were abundant, they could be drifting around space, sometimes ending up trapped within gas clouds. There, as new stars would be born, primordial black holes would eventually find their way into the star's cores. Even black holes the mass of Pluto would grow enormously within just a few 100 million years, a relatively short period of time in a star's evolution. So, even our Sun could have one, which the great late Stephen Hawking once suggested. If it hid a black hole about as massive as Mercury, we wouldn't even notice it, although it's very unlikely. But there's one method scientists think might help identify such cosmic containers for primordial black holes. For one, the so-called Hawking stars would be much more long-lasting. And to cool off, Hawking stars expand into red giants, something our Sun will do as it ages. But red giants with a tiny black hole inside would be a bit cooler than they normally are. Researchers have already detected about 500 abnormally cool red giant stars. To find out whether these stars hide primordial black holes within, scientists plan to observe the stars' unique vibrations as they pulsate, which could signify they indeed aren't ordinary red giants. And here's another mind-bending thought for you. Some believe that the mysterious dark matter that prevails in the universe is in fact a swarm of miniature, countless primordial black holes. And so while it's extremely improbable that a black hole like that would end up captured by a star, if there's an immeasurable number of them, at least some would. We'll have to wait till scientists figure that one out for us. But for now, that's all the time we have. Stay tuned here for more thrilling cosmic mysteries and fascinating discoveries. Let us know what you think about the enigmatic quasi-stars in the comments below. We read them all. And thanks for watching.